All right, so this is our second video, talk about the divergence theory. So the first video, we talk about why we want to use divergence theory and did a couple example. So for this video, we're going to also try to do a little bit more complicated example. Not really, but let's just take a look. Okay, so for the problem number 2, before we do that, just get everybody familiar with the source or sink. Okay, so it's kind of like a divergent type of the concept. So in here, right, so this is vector field. So for the P1, for the A's here, the P1, so this is the outgoing flow is bigger than since like here the it's getting longer and longer. So P1 is here. I know it's what is here. This is the outer. So we know this is the outward, right? So the outward here, then that means the divergence here, P1 is the positive. So because divergent P1 is positive, so we said P1 is this is a specific, we said this is the source. Okay, so the same way for here, the P2s here, this is the inward. So I know that from the divergence definition from the previous couple sections, we know the divergent P2 is going to be negative. So now we call this is the sink here. Okay, so like the same ones here for the B, for this graph here, we say the P1, this is what? This is the inward, right? So this is the inward, so that means the divergent P1 will be what? Will be equal to the negative. So if it's negative, so it's a sink. And then the P2 here is the outward. So the divergent P2 here is a positive. Or if it is a positive, then this is the source, right? So it's provided the flow, so going outside. So this will be a two very simple example, and I think then you can take a look by yourself to the part C to see P1 is the source or sink, and the P2 is the source or sink. Okay, let's take a look at this. Okay, so this one's here, the surface is getting a little bit complicated, right? So in here we have several surfaces here. It's a solid bounded by all these planes, right? So this one is S1, then the side one is S2, this side is S3, the back one is S4, then the bottom one, right, is S5. Oh my gosh, right? We have 5 surfaces here. If I want to use if I want to use the surface integration, probably be very, very tedious and complicated. And so let's take a look at the divergence series here. So the only thing we need to be careful about the divergence series, when we change it to the regular definite integration, we need to be careful about the bounds here. All right, so the divergence F here. Okay, so this is my P, this is my Q, this is my R's here. All right, so here, let's see here, so divergence here, the X here, so take the derivative to X for the P, so I have 2XZ. Take the derivative Q for the Y, I have 0. Take the derivative of R to the Z, I have 0. Wow, so this turns out to be pretty handy functions also. Okay, so now, so my surface integrations of this vector field over this 5 surfaces here, I can change to this solid, right? So this solid divergence 2xz. Now I'm integrating respect to the volumes, right? So now let's just try to see how do I put the volumes here. So this is 2xz here. All right, 2xz. All right, so let's do a dz first. How about that? We do dz dy dx. Okay, dz dy and okay, so dz dy dx. Okay, so for these here, I know that x plus 2z equal to 4. So 2z will be equal to 4 minus the x. So z will be 2 minus the x over 2, right? Okay, so z is from the 0 all the way to, right? So here z is from the all the way to here, right? So I know my z bound will be what? From the 0 to where? To 2 minus the x over 2, okay? So after that, I need to find the dy's here, right? So dy, okay, so this is the dy's, right? So dy's, okay, so now y is 2, 3, but dy, okay, so they said y equal to 3, x equal to 0. So dy, okay, so this one's here. So dy is just from the 0 to where? These are two threes here. Then the dx here, right? So the dx is from when the z equal to 0, x equal to 4, right? So when z equal to 0, x equal to 4, so the dx here will be 0, 4. Okay, so then we change this integration to a pretty easy integrations, right? So you just integrate the z and substitute and then become a very, very typical, we call this a definite integration, triple integration. So if you take a look, if you carry out this is what I have is 16th here. So it turns out pretty good. Okay, now let's take a look at this one here. So this one, so even looks is pretty complicated, but I think it's not too bad. Okay, so this is my vector fields here. S is the surface of the solid bounded by the cylinder, x equal to the y square, and the plane, x plus z. So basically, I have two surfaces here, three surfaces. This is S1, the body is S2, and the bottom is S3 here, right? So now I think maybe I will use the divergence theory to simplify the integrations here. So this is a P, this is a Q, this is a R. Okay, so rho P, rho X would be Y, rho Q, rho R is 0, rho R, rho Z is 2Z's, right? So okay, so I got equal to Y plus 2Z. So it turns out, that's why I say I like the divergence theory, because the divergence of f is a scalar function. It's way easier to handle than the vector functions here. All right, so now here, this is use integrating the vector field over this solid here. So it will be equal to this whole solid E. Now I have y plus 2z dv's here. All right, so now let's take a look. How do I want to put the integration bound? This is where in the chapter 15 when we talk about the triple integrations and how to set the limits. All right, so here this is y plus 2z here. All right, let's take a look. How about the first one? Let me integrate to the dz's here. All right, so dz, because I have this one here. All right, so that means z is equal to what? Z equal to the 1 minus the x, right? Okay, so z is from the 0. So the dz here is from the 0, right? So dz is from the 0 to where? To the 1 minus x. Okay. Now the next one, since I have 1 minus x here, the next one, Let's try see how about if I want to integrate dx here. Okay, so if I want to integrate dx here, all right, so the x is equal to the y squares, right? So x equal to is this curve, right? So this is the curve. So x is from, so where is my, so that means I'm integrated here, right? So this is 1, so right? So that means my x is going to start from the y square all the way to where? All the way to 1, okay? So the last things here is, and then finally, I need to go to the dy here. Okay, so here, this is the y-axis, right? So that means here is 1 and this is negative 1, right? Because this is the curve cover that. So what is my dy here? Dy here will be the negative 1 and 1. So for this one, we need to be a little bit careful, right? So you look at find the divergence is pretty easy. Now after you find the divergence here, you take the derivative, you take the integration respect to the z. All right, so it's from 0 to this plane, right? So if you want to, so it's from 0 to this plane, and this plane is z equal to 1 minus x. Then the dx here, the x and y is this red curve. So x is from where to where? X is from y squared to 1. Okay, then the dy is here. You look at the y-axis from 1 to negative 1. So this one's here, and even we have several variables, but the integration is just like the definite integrals here. So if you are very patient and not make any algebra mistake, you will get the final answers should be, I got it is 32 over the 105. Okay, so just be very, very careful about the algebra and the upper bound, lower bound. So the most important for those here, you need to make sure you get the upper bound, lower bound correctly based on the graphs, based on the solid here. All right, that's it. That is for the divergence series. Just remember, divergence series simplify the surface integration a lot. Especially you have some closed solid. They have many, several surfaces around. Then you might want to use divergence series to simplify it. All right, that's it. Have a good day. Okay, bye.